Hello, in this video I'm going to run through a question on air resistance. If you recall back to when we were talking through our non-fundamental forces, our contact forces, the air resistance stuff, it tends to get treated separately to our friction, to our normal reaction force, to our tension. And we have a lot of these questions where we look at things like terminal velocity, and it gives us a relationship for the force due to the air resistance as a function of velocity. So that's what we've got going on in this question. So what I'm going to do is run through what's a fairly straightforward question, just in the sort of standard fashion to get the answers as if we were doing it in an exam. And then we'll see if we can find anything interesting to sort of pick apart in a bit of a deeper dive later on. Right, so we're starting off just stating two factors that affect the magnitude of the drag force acting on an object falling through the air. Right, there's quite a lot of things we could state there. I mean, you've got the shape of the object that's falling. If you've got a very large surface area, you're going to get more drag. You've got the density of the medium, in this case the air, the density of the air that you're moving through. You've got the velocity, the faster you're moving, or I should say the speed really, because it doesn't matter on the direction. The faster you're moving, the greater the magnitude of the drag force. So two of those three would be the obvious ones to go for. Right, now we're moving on to a specific case of a skydiver of total mass 75 kilograms falling vertically towards the ground. So they're giving us this air resistance drag force D, and that is in newtons acting on the skydiver, and it's given by this equation. So this is what we're saying, they'll give us some relationship for drag as a function of velocity or speed. Draw the arrows to represent the weight and the drag force, right? So not a lot to do with that. Weight is always straight down from the center of mass, and then the drag force is going to be opposite to the direction of motion, which in this case is upwards. So that's quite straightforward. Calculate the weight of the skydiver. Well, again, easy enough. Weight is just going to be the mass times acceleration due to gravity, so 75g. Which we can say is what, 736 newtons. We're using 9.8 for g. At a particular instant, the speed of the skydiver is 20 meters per second. Calculate the instantaneous acceleration of the skydiver. Okay, so if we're moving at 20 meters per second, then that means we can work out what d is. It's going to be 0.3 times 20 squared. So that is 400 divided by 10 multiplied by 3, which is 120 newtons. So we can use Newton's second law, use F equals ma. We've got 736 newtons going downwards, 120 newtons going upwards, and that is going to be 75 times the acceleration. So just plugging all of that into the calculator, we get the acceleration is 8.2 meters per second squared. So far so good. State the relationship between the forces W and D when the skydiver reaches terminal velocity. Well, they'll be equal to each other. That's the point of terminal velocity. The velocity isn't changing anymore. That's why it's called terminal velocity. So if the velocity isn't changing, then we've got no net force acting on the object. So W must be equal to D, because they're the only two forces that we're considering in this particular case. Determine the terminal velocity of the skydiver, right? So this means that we need D to be equal to 736, then equal to the weight, and that is 0.3 v squared. So we're just dividing by 0.3 and then taking the square root, which gives us that v is 49.5 meters per second. Yeah, we might want to go round it to 50, but there you go. So straightforward enough going through all of those. Something has jumped out that could be of interest here in taking a closer look at this equation that we've got here for the drag. So we're going to be able to, when we put it into Newton's second law, we're setting up a first order differential equation. So let's see if we can do anything with that. Right, I'm going to hide a lot of this because this could be quite a lot of work. So let's remove some of these and just go for a blank sheet. So off of Newton's second law, we've got, so we're putting stuff into our F equals ma. So our force is our weight. I'm going to keep it at 75g because it's just a bit easier to write. Minus d, which was 0.3 v squared. And that is equal to 75 dv dt. We change the acceleration into our calculus form. Now we've got a first order differential equation, and if we can solve this, we're going to get a function of velocity. Velocity is a function of time. So let's see if we can actually solve all of this. So let's separate our variables here. So we're going to have the integral of dt is going to be equal to the integral of 75 dv divided by all of the stuff, 75g, all the stuff on the left hand side, 0.3 v squared. Right, and that's going to be going from 0 to t and then from 0 to v. Okay, so this isn't a trivial integral to do because we've got v squared on the bottom. So it is going to end up being something to do with natural logs, but we can't just say it's a straight natural log function because we've got no v at the top. So we're going to have to separate this into partial fractions, and then we'll see where we go from there. So let's do a separate bit of partial fraction work. So let's ignore the 75 at the top because that can go on the outside of the integral. So let's put that 75 there and just get rid of that. So we've just got a 1 now on the numerator. And we're going to try and separate out 1 over 75g minus 0.3 v squared. And we're going to want to put that into two fractions. And this is difference of two squares on the denominator. So that's going to make things a bit easier. So we can have an a divided by root 75g. So we've got to do the square root of each one of these terms. Let's do a minus there. Square root of 0.3 times v. And then we're going to have a b divided by, it's going to be the same thing but with a plus in the middle. So square root of 75g plus the square root of 0.3 multiplied by v. Okay, so we're going to be cross multiplying these and then working out what a and b are. So we've got 1 is equal to a times the bracket with the plus in the middle plus b times the bracket with the minus in the middle. It just saves me writing it all out again. We can see what these brackets are. So when, let's set one of these equal to 0. So say we were going to have this b bracket equal to 0. We're going to need v to be equal to square root of 75g divided by the square root of 0.3. Because of course when we put that in for v here, the square roots of 0.3 are going to cancel and then we get nothing in the bracket. And then this is going to allow us to work out what a is, because a would then be, it's going to be 2 lots of root 75g. So, and we'll have the reciprocal of that. So a is going to be 1 over 2 times the square root of 75g. And what's going to happen with b? So if we're going to want to do the same thing with a, we'll have to have a negative version of this v. We just have this v again, but with a minus sign at the front, which means it will add up in the same way, and that's actually going to be identical to b. We're going to get the same thing happening there. So a and b are actually the same. That should help things considerably, I would have thought. So we've now got what our two fractions are. So going back to our integral, we can tidy up the left-hand side and just say, well, that is t. And then we've got a lot of factors kicking around here, because that square root 2 square root 75g we can take on the outside as well. So let's have all of these constants that we've got kicking around at the moment outside of our integral. Put that on the outside. And then we need to integrate from 0 to v our two fractions with respect to v. Let's just section off all of that work that we did up there. So our two fractions are going to be 1 divided by the bracket with the minus sign in the middle, and 1 divided by the bracket with the plus sign in the middle. So again, just save writing out all of these root 75s and everything all the way through it. So we can leave that constant there at the start. Still got our 75 over 2 root 75g. And now we're going to have two log functions going on here. So one of them is going to be a positive function and the other one's going to be a negative function. And we've got to divide by that square root of 0.3 as well. So this is going to leave us, right, let's put in the 1 over square root of 0.3 because that's going to be in both of them. And then we can do the right hand fraction minus the left hand fraction, which means we're going to be able to divide them. So we're going to have the log of the function with the plus and then divided by the one with the minus. That's all we're going to get if we're typing all of those in. So let's actually write it in this time. Square root of 75g plus square root of 0.3 times v, and then the same thing again, but with the minus in the middle. So if we can rearrange all of this and make v the subject, which isn't going to be that hard to do, then we've got ourselves a function of velocity with respect to time. But let's do this in a couple of steps because there is quite, well, actually we're going to have all of the multiplying all of this, or dividing by it really, to get t multiplied by all these constants here. Then we're going to do e to the power of that. Yeah, let's do that step first and then just sort of leave it there for the moment. Oh, and we can multiply by this denominator as well, I think. So doing one quick step, we're going to have the top bit of the log function, writing this a bit larger because we're getting near the end, and that is going to be equal to the denominator multiplied by our exponential function. So that's going to be multiplied by e to the, right, we're going to have all of this upside down. So 2, and we have a t there, square root of 0.3 square root of 75g divided by 75. Okie dokie. Now we need to group our v terms together and our non-v terms together, right? So we're going to be adding that over, taking that off, right? So we're going to have a -1 and a +1 on these. So v, the last bit of rearranging, we've got the 75g's at the top, we've got the 0.3's at the bottom, and then we've got these two big, so e to the, well, I'm going to call it a, I think, at -1, and then e to the at +1, where a equals 2 root 75g root 0.3 divided by 75. So that's quite an involved piece of calculus and algebra there, but it's not that difficult. I mean, this is all stuff that you cover in pure maths. I mean, you know, you do these partial fractions, you do integrals of log functions, and then we've just got to have some solid algebra in order to rearrange everything and make V the subject. So there's not actually anything here which is beyond A-level syllabus. This is, you know, fairly standard pre-university maths. And it's come out with, well, let's see. I mean, hopefully I've actually got this correct. Let's plot this out. If we plot this graph, hopefully it will show us the answers that we got in when we were just working through normally, but we're also going to have a bit of extra depth there because we've got a whole velocity function. Okay, so I've taken a while to type all of this into Desmos, which is the sort of standard graph plotting website that I use, and yeah, this is looking good. So I've typed it out in 2 bits. I've put in that A just to simplify it, make sure that our, you know, the function doesn't look too complicated. It's nice to write it out in 2 chunks. So defining what A is, that's the, you know, part of that power on the exponential, and then typing in the rest of the function. And we can see this is the same as we had when we just worked out the terminal velocity. If you remember in, I think it was the penultimate part of the question, it's like, okay, what is the terminal velocity of the Skydiver? And we got 49.5. Well, lo and behold, here we are with this terminal velocity at 49.5. So as t increases on the x-axis, I know this is saying function of x, but x is our time. So yeah, as it's increasing, we're hitting terminal velocity in under 20 seconds. We're also seeing that it's taking quite a while for this drag to kick in. The gradient here, as we'd expect at the origin, is going to be, you know, we want a gradient of g because we haven't picked up any drag force until it starts moving. Then the drag force is going to keep increasing, but it's not really kicking in at all until we've got up to, you know, maybe 2 or 3 seconds here. And then it doesn't really have much of an effect until, okay, maybe here, once we've got up to 40 meters per second or something like that, then we're really getting that reduction in acceleration. You know, thinking the acceleration here is the gradient all the way around. I mean, it's dropping off very rapidly as we approach up to 10 seconds of travel. But this function is great now because not only can we see the variation of the velocity, that means we can see the distance traveled. You know, we could do numerical methods on this. I mean, we could integrate it in order to work out the area under the curve, or we could use numerical methods, which would be probably easier to do. When we start looking at the coding videos, we could code this up, do a trapezium rule or something similar in order to work out the area under here, see how far he's actually traveled, how long will it take the parachutist to hit the ground, or at least how long will it take him to reach the point where he needs to deploy his parachute in order to bring his velocity back down. So yeah, it does give us a lot more information having that power to be able to solve those differential equations. And we can do this with any application of Newton's second law. Whenever we're using F equals ma, we can always delve into that differential equation, and then yeah, use that to pull out velocity functions, displacement functions. That's why it's so important to be able to, well, to have really solid algebra and really solid calculus skills. So yeah, I think that's been quite helpful going through all that and pulling out more complexity into what was a very simple question. Okay, you want to understand the physics of, well, why are we reaching a terminal velocity? How can we calculate the terminal velocity? But the more power you've got in your math skills, the more insight you're going to get into problems of motion of this type.